All right. Now, the combined gas law. How's this? We're not going to do any problems with the combined gas law. You remember before we had PV equals PV? Right? Everybody remembers that? What if we put both sides over T like that? That's a combined gas law. We can get all three of those laws out there. PV equals PV, that's Boyle's law, right? If I take the P out, I get Charles's law. If I take the V out, I get Gay-Lussac's law, right? Just know that you can combine those three laws into one. How about if we don't do any calculations using this? Is that fair enough? Because I've learned that you guys really don't like solving this. It gets into more math than you guys really want. All right, what we do need to talk about is the relationship between the volume of a gas and the number of moles that you have. Because we all love moles, don't we? So just stop digging up my yard. Now, we're going to come back to this idea right here, 1 mole of gas is 22.4 liters. And it only occurs when you're at STP. STP is standard temp and pressure. And we'll get there, okay? We're going to talk about standard temperature and pressure, and we're going to talk about this relationship of 1 mole of gas being 22.4 liters. By the way, how big is 22.4 liters? Anybody know how much 22.4 liters is? Do you own anything that's roughly 22.4 liters? Like in the same ballpark as 22.4 liters? You're thinking. All right. How much is a liter compared to our American unit? What's a liter equivalent to? How much is a liter? It's about a what? 1 liter is roughly a quart. 1 liter is roughly a quart. How many quarts in a gallon?
4.
4 quarts in a gallon. So 20 liters would be about 5 gallons. So this is a little bit more than a 5-gallon bucket. Okay? So when we talk about 1 mole of gas, just think about carrying a 5-gallon bucket around, empty. Well, it's not really empty. It's got air in it. That's a good joke for today. I didn't do this in the other class. What does an optimist say?
Half full.
Half full. Pessimist. Half empty. Chemist. Always full. Why? Well, it's half liquid and half gas. It's still full. It's just not full of liquid. Isn't that a much better way to think about it? So your glass is always full. That's a great way to think about it. Let's think.
It's not necessarily how much you want it to be full of, though.
Debbie Downer over
She
here.
ruined it for you.
Really? Holy cow. It's full of things that you need it to be full of, though. Like oxygen, right? Okay. That's enough about that for today. Okay. Here's Avogadro's law. Lots of laws in this chapter. And what did I tell you guys last week for all these laws? Don't memorize them. I'll give them to you on it when we take the final, right? When all this is on the test, I'll give you a sheet that has all these equations on it. Fair enough? Learn how to use them. Here's Avogadro's law. And this law should make easy sense to you. If the pressure and the temperature remain constant, when I add more moles of gas here, the volume has to change. Now, we didn't do this last weekend when we went outside. When we added more moles of gas, because our volume stayed constant, what happened to our pressure? It went up, didn't it? Now, had we wanted the pressure to remain constant, how could we have made the pressure stay constant when we added more people to our area? Expand the volume. If you make the area bigger, the people don't bump into the sides as much anymore, right? Our gas molecules. Okay? So, volume and number of moles, the ratio. What are you doing over there? It's constant, isn't it? Okay? This is Avogadro's law. So where do you think we're going with Avogadro's law? We're coming back to moles, right? Because we love moles. Moles are good. Okay? And this is how he really figured out about his law of how many atoms or molecules are involved. Okay? So this is, if you give it a problem like this, you solve it just like we've been doing, cross multiply. You guys can knock this out. You guys are all good at this. Okay? Let's just do one just for practice. But before you do it, think about it. The number of moles does what? It does what? It goes up. It almost doubles, doesn't it? Not quite. So the volume has to do what? The volume has to go up too, doesn't it? Well, we start off with 1.5, so that means that what? This answer right here. So you just went from having, without even using my calculator, I went from having a 33% chance of getting this problem right to having a 50% chance of getting it right. And if I think about it a little bit more, the number of moles goes up a lot, the volume must go up a lot. I'm going to guess the answer C, even without using my calculator. Won't y'all verify that I'm right? How you going to verify that I'm right? Well, you got to use Avogadro's law, right? I'm right. So, what's our initial volume? 1.5 liters. And how many moles do we have at 1.5 liters? 0.75 moles. We don't know V2, but we do know that we have 1.2 moles. So if I add more moles, the volume must increase. Multiply these two, divide by this one, should get 2.4 liters. Okay? Does everybody see how we got that? We're all good? Okay. Now, this idea of 1 mole equaling a certain volume comes out of this, okay? If the pressure and the temperature are at standard conditions, and for this work, standard conditions is 0 degrees C, whoops, and 1 atmosphere. Nobody works at these conditions because nobody wants to work when it's freezing, right? Not in the lab. But at 0 degrees C and 1 atmosphere, this is true. These are called standard temperature and pressure. If you are at standard temperature and pressure, 1 mole of gas equals 22.4 liters. Does it say that it matters what kind of gas you have? Does it matter if it's oxygen or nitrogen or helium? Does it matter? It does not matter at all. This is called the molar volume for gases at STP. 1 mole equals 22.4 liters. If you're at STP, it does not matter which gas you have. And because these two things are equal for these gases at STP, look at what we can do. We can write conversion factors. Yay! This is the last time we're going to do conversions. You better enjoy it. Here we go. So it doesn't matter if you have 1 mole of helium, oxygen, or nitrogen. 1 mole of helium is 4 grams, 1 mole of oxygen is 32, and 1 mole of nitrogen is 28. The masses change, but the volume doesn't change because you're at standard temperature and pressure, okay? As long as you're at standard temperature and pressure, this holds true. Now, let's work a couple of conversion problems. So what do we say? 1 mole equals 22.4 liters. Can you solve this problem? It's a one-step conversion. Pretty straightforward, though. If we learned our conversions way back then. So what do we have? 2.75 moles of N2. What's going to go on bottom? Has to be moles of N2, doesn't it? Well, 1 mole of N2 is what? 22.4 liters of nitrogen. So 2.75 times 22.4, and we get 61 point, what? 6?
6.
Okay.